Now we introduce a new quantity called torque acting on a rigid body about an axis. Let us consider a rigid body rotating about a fixed axis as seen in the figure. For a vertical axis of rotation, we can neglect the effects of the weight of the body on its motion. As everyday experience shows, we can change the state of motion of such a body, for example when we open or close a door, by applying a force on it provided the line of action of the force is not parallel with the axis of rotation. In other words, if an arbitrary force F' is exerted upon a rigid body rotating about a fixed axis, only its component F lying in the plane perpendicular to the axis of rotation can have an effect on the rotation of the body. Then we can examine a force F acting on a body with the line of action in the plane perpendicular to the axis of rotation passing through the plane at the point O. Everyday experience also shows that the force F can only have effect on the rigid rotation if its line of action and the axis of rotation do not intersect, that is the distance d between the point O and the line of action of the force does not vanish. The perpendicular distance d from the axis to the line of action of the force F is called the lever arm of the force F about the axis of rotation. We define the torque tau of the force F acting in the plane perpendicular to the axis of rotation by the magnitude of the force F times the lever arm d of the force. By convention, counterclockwise torques are positive and clockwise torques are negative. The unit of torque is given by the unit of force times the unit of length, which is the same as the unit of work, that is the unit of mass m times the unit of length L times the unit of time t to minus 2, times the unit of length L. The SI unit of torque is therefore equal to Newton meter. We can perform the following experiment with a spool rolling on the floor to demonstrate the importance of the relative position of the line of action to the instantaneous axis of rotation for the effect of the force acting on the rotating body. We can pull the thread wound on the spool such that the angle measured between the direction of the line of action and the floor is either greater or smaller than a critical angle. If the force F is applied on angles below the critical angle, then the spool will roll towards the person pulling the thread. If the force F is applied on angles above the critical angle, then the spool will roll away from the person pulling the thread. In the figure, the point O denotes the contact line of the spool and the floor serving as the instantaneous axis of rotation for the spool. In the first case, the force F rotates the lever arm OP in clockwise direction about the instantaneous axis of rotation, that is the torque tau of the force F about the axis of rotation is negative. In the second case, the force F rotates the lever arm OP in counterclockwise direction about the instantaneous axis of rotation, that is the torque tau is positive. By applying the concept of torque, we can formulate the condition for the equilibrium of rigid bodies free to rotate about a fixed axis, such as levers used to multiply force. Let us suppose that a system of forces F1, F2, ellipsis, Fn is exerted on a rigid body free to rotate about a fixed axis, where the lines of action for all the forces lie in a plane or planes perpendicular to the axis of rotation. In the figure, the point O denotes the intersection of the axis and the plane or planes of the lines of action, and D1, D2, ellipsis, Dn are the lever arms of the corresponding forces about the axis of rotation. The rigid body under the influence of these forces is in equilibrium if the algebraic sum of the torques τ1, τ2, ellipsis, τn of the forces F1, F2, ellipsis, Fn about the rotation axis vanishes. Here each torque tau is given by the magnitude of the force Fi times the lever arm di of the force Fi. Archimedes' law of the lever is just a special case of this condition for n equal to 2, stating that the weights suspended from a lever are in balance at distances inversely proportional to their magnitudes. If the force F1 represents the weight suspended from the left arm of the lever at the distance d1 measured from the pivot of the lever or its fulcrum, and F2 is the weight suspended from the right arm of the lever at the distance d2 from the fulcrum, then we can write that the magnitude of the force F1 times the lever arm d1, minus the magnitude of the force F2 times the lever arm d2 vanishes. The second term in the sum is negative since the force F2 produce a clockwise torque on the lever. This formula is equivalent to the equation stating that F1 times d1 is equal to F2 times d2, which can be demonstrated with the setup shown in the figure. That is, 2 units of weight times 6 units of length is equal to 3 units of weight times 4 units of length. This law immediately follows from the result already obtained in the discussion on the superposition of forces acting on rigid bodies because the forces F1 and F2 can be replaced by the force F with a line of action passing through the point O. Since its line of action has an intersection with the axis of rotation, the net force F cannot produce rotation. Another important application of the concept of torque is related to the work done in the case of rigid rotation. If a rigid body turns through a small angle delta phi about the axis passing through the point O under the influence of the force F applied on the body at the point P, then the point P has a small displacement delta S given by R times delta phi, where R is the distance between the points O and P. The work delta W done by the force F can be written as the magnitude of the force F times the displacement delta S times cosine alpha, where alpha is the angle between the tangent to the circular trajectory of the point P and the line of action of the force F. This expression can be written as F times R times delta phi times cosine alpha, where R times cosine alpha is equal to the distance d between the point O and the line of action of the force F. Then the right-hand side gives the magnitude of the force F times the distance d times the angle delta phi. Since the distance d is the lever arm of the force F about the axis passing through the point O, F times d is equal to the torque tau of the force F about this axis. As a result, the work delta W done on the body by the force F can be written as the product of the torque tau and the angle delta phi. In the case depicted in the figure, this work is positive, that is, the torque tau is positive. The work done by the force minus F is negative because the torque tau is negative. If the angle delta phi tends to 0, then we obtain the infinitesimal work dW given by the torque tau times the differential of the angle phi. For a finite rotation through the angle phi, the total work done by the force F can be written as the integral of the torque tau of the force with respect to the angle phi. If the torque is constant, then the work W is simply equal to the torque tau times the angle phi. Now we generalize the concept of torque about a point and interpret it as a vector quantity. Let us suppose that a rigid body is free to rotate about the point O, and the force F is applied on the body at the point P. If theta denotes the angle between the direction of the position vector r of the point P with respect to the point O and the line of action of the force F, then the lever arm d of the force F about the point O can be written as the length of the position vector r times sine theta. By definition, the torque tau of the force F about the instantaneous axis of rotation passing through the point O is given by the magnitude of the force F times the lever arm d of the force, which is equal to r times F times sine theta. If we interpret the right-hand side as the magnitude of a cross product, namely the cross product of the position vector r and the force F, then we can generalize the concept of torque as follows. The torque tau of the force F applied at the point P about the point O is defined by the cross product of the position vector r of the point P with respect to the point O and the force F. Since the cross product of two vectors also gives a vector, torque is defined as a vector. Its direction perpendicular to the plane spanned by the vectors r and f, and its orientation is determined by the right-hand rule. The unit of torque is the unit of length times the unit of force as stated in the definition of the scalar-valued torque. That is the unit of mass m times the unit of length L times the unit of time t to minus 2, times the unit of length L, which has the SI unit of Newton meter. We can attach a Cartesian coordinate system to the center of rotation O where the instantaneous axis of rotation is the z-axis. Then we can write the x component of the torque tau about the center of rotation as the y-coordinate of the point of application P times the z component of the force F applied at the point P, minus the z-coordinate of the point P times the y-component of the force F. Similarly, the y-component of the torque tau is given by the difference between the z-coordinate of the point P times the x-component of the force F, and the x-coordinate of the point P times the z-component of the force F. Finally, the z-component of the torque tau is equal to x times Fy, minus y times Fx. By applying the definition of torque as a vector, we can also state that the torque of an arbitrary force F about an axis passing through the point O is given by the component of the torque tau parallel with the axis of rotation. Since we have chosen the Cartesian coordinate system such that its z-axis is the instantaneous axis of rotation, the torque of the force F about the z-axis passing through the point O is equal to the z-component of the torque tau, which can be written as the z-component of the cross product of the position vector r of the point of application P and the force F. In other words, it is given by the x-coordinate of the point P times the y-component of the force F, minus the y-coordinate of the point P times the x-component of the force F. If the line of action of the force F exerted on the body is in the xy plane or in any plane parallel with the xy plane, then the z-component of the torque tau can be written in the form introduced in the scalar definition of torque. For the z-axis as the axis of rotation and the x-axis perpendicular to the line of action of the force, the x-component of the force F vanishes. As a result, the formula describing the z-component of the torque reduces to the product of the x-coordinate of the point of application P and the y-component of the force F. For example, let us apply the forces F1 and F2 at the points P1 and P2 such that their lines of actions are perpendicular to the x-axis. Then the z component of the torque τ1 of the force F1 is given by the coordinate x1 of the point P1 times the y component of the force F1. Since x1 is equal to minus the lever arm d1 and F sub 1 y is equal to minus the magnitude of F1, we obtain F1 times d1, which is positive, indicating a counterclockwise rotation. The z component of the torque τ2 of the force F2 is given by the coordinate x2 of the point P2 times the y component of the force F2. Here x2 is equal to the lever arm d2 and F sub 2 y is equal to minus the magnitude of the force F2. Then tau z can be written as minus F2 times d2, which is negative, indicating a clockwise rotation. We also note that neither the z component of the force, nor the z coordinate of the point of application appear in the expression describing the z component of the torque tau. This involves the previously mentioned fact that neither the component of a force parallel with the axis of rotation, nor the coordinate of the point of application of the force specifying its position along the axis have a role in the rotation about the axis. By applying the general definition of torque, we can formulate the condition of equilibrium for a rigid body free to rotate about a single fixed point. Let us consider an experiment where we stick a solid cylinder upon a rod tapered to a point, as seen in the figure. If the diameter of the rod is smaller than the one of the bore at the bottom of the cylinder, then the tip of the rod is only one contact point with the cylinder denoted by the letter O. As a result, the cylinder is free to rotate about the contact point O, which is a fixed point of the rigid body and also called pivot point. Since the rod is in a vertical position, the cylinder is subjected to only its own weight and stays at rest. If we apply the force F1 on the cylinder at the point P1 described by the position vector R1, the body will turn about an axis passing through the pivot point O. However, by applying one or more forces on the body, for example the forces F2 and F3 with the points of application P2 and P3 described by the position vectors R2 and R3 respectively, we are able to maintain the equilibrium of the cylinder. We can perform an experiment with dynamometers attached to the points P1, P2 and P3 of the body and measure both the magnitudes and the directions of the forces applied on the body while it stays at rest. If the cylinder is in equilibrium for given position vectors R1, R2 and R3 of the points of application of the forces F1, F2 and F3 with respect to the pivot point O, then the experiment can demonstrate that the cross product of R1 and F1, plus the cross product of R2 and F2, plus the cross product of R3 and F3 vanishes. By definition, the cross products in the left-hand side of the equation are the torques τ1, τ2 and τ3 of the forces F1, F2 and F3 applied at the points described by the position vectors R1, R2 and R3. The condition therefore states that the vector sum of these torques must vanish in equilibrium. The general formulation of this condition, which can also be demonstrated by experimentally for a finite number of forces, is the following. For a system of forces F1, F2, ellipsis, Fn applied on a rigid body free to rotate about a pivot point O, the body is in equilibrium if the vector sum of the torques τ1, τ2, ellipsis, τn about the pivot point O vanishes. Here the torque τi for all I from 1 to n, is equal to the cross product of the position vector Ri of the point Pi with respect to the pivot point O, and the force Fi applied at the point Pi. In this condition, the reference point O is the pivot point, that is a fixed point of the rigid body around which the body is free to rotate. However, we can also choose an arbitrary reference point O' in the body, and write the torque τi in the terms of the position vector R'I with respect to the new reference point for all I from 1 to n. Then we can write the vector sum in the condition as the sum of the cross products of the position vectors R'I and the forces Fi from I equals 1 to n, where each vector R'I can be written as the vector sum of the vector R0 and the original position vector Ri. As the figure shows, R0 denotes the vector pointing from the new reference point O' to the pivot point O. The right-hand side can be written as the sum of the cross product of the vector R0 and the force Fi from I equals 1 to n, plus the sum of the cross product of the vector Ri and the force Fi from I equals 1 to n. The second sum is simply the original sum appearing in the condition. Since the vector R0 does not depend on the index I, it can be factored out in the first sum. Then we obtain the cross product of the vector R0 and the net force F acting on the body defined by the vector sum of the forces Fi for all I from 1 to n. This result shows that the net torque on a rigid body by a system of forces is only independent of the reference point, if those forces result in zero net force. We can apply these results to determine the torque of a pair of forces or a force couple. Let us suppose that the force couple F and minus F is exerted on a rigid body at the points P1 and P2, where the body is free to rotate about its pivot point O. Here R1 and R2 denote the position vectors of the points of applications for F and minus F with respect to the center of rotation O. The torque tau of the force couple about the pivot point O is given by the vector sum of the torques of the forces F and minus F about the point O, which can be written as the cross product of the position vector R1 and the force F, plus the cross product of the position vector R2 and the force minus F. Since the cross product is linear, the second term is equal to minus the cross product of R2 and F. Then we obtain the cross product of R1 minus R2 and F. The difference between the position vectors R1 and R2 denoted by R is equal to the vector pointing from the point of application P2 of the force minus F to the point of application P1 of the force F. As a result, we can write the torque tau of the pair of forces as the cross product of the vector R and the force F, which is independent of the position of the reference point O. The direction of the torque is perpendicular to the plane of the pair of forces with the orientation determined by the right-hand rule of the cross product, and its magnitude is given by the magnitude of the force F, times the length of the vector R, times the sine of the angle theta between the vectors R and F. Since the length of the vector R times sine theta gives the distance d between the lines of actions of the forces, we can state that the magnitude of the torque of a pair of forces is equal to the magnitude of any of the forces in the pair, times the distance between the lines of actions of the force couples. Only the magnitude and the direction of the torque determined by the cross product are relevant to the effect of the pair of forces on the rotation of the rigid body. The points of applications of the force couple and the individual quantities R, F and minus F do not play any role in the effect. In other words, two pairs of force are equivalent if their torques have the same magnitude and direction. For example, let us consider the force couple F and minus F applied at the point P1 and P2 of a rigid body. By introducing the auxiliary forces F' and minus F' cancelling each other out, we can derive the pair of forces F1 and minus F1 as the vector sums of the first force couple and the auxiliary forces. The force couple F and minus F applied at the points P1 and P2 is equivalent with the force couple F1 and minus F1 with the same points of application because the auxiliary forces do not have contribution to the torque of the force couple. If we translate the pair of forces F1 and minus F1 such that their points of application are at the points Q1 and Q2, then the force couple F1 and minus F1 applied at the points Q1 and Q2 is still equivalent with the original force couple. This can be seen from the fact that the magnitude of the force F times the distance d between the lines of actions of the forces F and minus F, is equal to the magnitude of the force F1 times the distance d1 between the lines of actions of the forces F1 and minus F1. We can even talk about the equivalence of force couples in a more general case. Two force couples having the same torque are equivalent even if their lines of actions lie in two distinct parallel planes. This statement is illustrated by the experiment with the apparatus shown in the figure. A thick beam is suspended from three wires passing through fixed pulleys and held in equilibrium with the weights G1, G2 and G3 hanging on the other ends of the wires. The weight G2 is connected to a rod by the wire and the rod attached to the beam. Two further weights are suspended from the beam and another rod attached to the beam in order to produce force couples acting on the beam. As we can see, two sets of weight are used in the series of the weights G1, G2 and G3, light ones and heavy ones. The light weights are only applied to achieve complete balance of the net forces exerted on the beam, and their contribution to the effect of the heavy weights is negligible. In this setup, two force couples are exerted on the beam, the force couple F1 and minus F1, and the force couple F2 and minus F2. Since the beam is in equilibrium under the influence of the two force couples and the net force of the force couples vanishes, the net torque rotating the beam must vanish as well. This can immediately be seen if we determine the torques due to the two force couples. The magnitude of the torque tau1 produced by the pair of forces F1 and minus F1 acting on the beam is equal to the magnitude of the force F1 times the distance d1 between the lines of action of the forces F1 and minus F1. As the figure shows, its value is given by 2 units of weight times 6 unit of length. By definition, the torque tau1 is perpendicular to the plane P1 spanned by the force couple F1 and minus F1, and its orientation is given by the right-hand rule producing a clockwise rotation. The magnitude of the torque tau2 produced by the force couple F2 and minus F2 acting on the beam is equal to the magnitude of the force F2 times the distance d2 between the lines of action of the forces F2 and minus F2. Its value is given by 4 units of weight times 3 units of length. The torque tau2 is perpendicular to the plane P2 of the force couple F2 and minus F2, and its orientation shows that it produces a counterclockwise rotation. Since the planes P1 and P2 are parallel, the torques tau1 and tau2 are opposite in direction. At the same time they have the same magnitude, that is the torque tau1 is equal to minus the torque tau2. Then the torque due to the pair of forces F1 minus F1 is compensated by the torque due to the force couple F2 minus F2 as we expected for the system in equilibrium. The equilibrium of the beam shows that the effect of the force couple F2 and minus F2 is equivalent to the one of the force couple F3 minus F3. The pair of force F3 and minus F3 can compensate the effect of the force couple F2 and minus F2 because they have the same points of applications while point in opposite directions, and their torques are equal in magnitude but opposite in direction. Indeed, the magnitude of the torque τ3 due to the pair of forces F3 and minus F3 is given by the magnitude of the force F3 times the distance d2 of the line of actions of the force couple, or 4 units of weight times 3 units of length. The torque τ3 is perpendicular to the plane P2 of the forces F3 and minus F3, and its orientation shows that it produces a clockwise rotation. The torques τ1 and τ3 therefore have the same magnitude and direction, that is the torque τ1 is equal to the torque τ3. In the experiment, we have demonstrated that the force couple F2 and minus F2 lying in the plane P1 is equivalent to the force couple F3 and minus F3 lying in the plane P2 parallel with the plane P1. This result shows that only torque has a role in the effect of a force couple, and this effect will not change if the torque is translated parallel to itself. In other words, the starting point of the torque vector can be translated to an arbitrary point of the rigid body. Such a vector is called free vector as opposed to the bound vectors like the position vector, which cannot be translated. Then we conclude the theorem stating that a system of force couples acting on a rigid body is equivalent to a single force couple having the torque given by the vector sum of the torques due to the individual force couples. Here the net torque and the torques due to the force couples are determined with respect to a given reference point. We can apply this theorem to another one on the reduction of a general system of forces. When we studied the superposition of forces applied on a rigid body, we demonstrated that a system of n forces acting on the body can be replaced with a single resultant force and n pairs of forces or force couples. Now the theorem formulated here states that these n force couples Fi applied at the point Pi and minus Fi applied at a reference point O for I from 1 to n, are equivalent to a single force couple having the torque τ given by the vector sum of the torques of the individual force couples. That is, τ is equal to the sum of the cross products of the vectors Ri and Fi, where Ri is the vector pointing from the point of application Pi of the force Fi to the reference point O. Then we can state the following theorem. The system of forces F1, F2, ellipsis, Fn acting on a rigid body is equivalent to the net resultant force F and a force couple producing the torque τ. Here the resultant force F is given by the vector sum of the forces Fi from I equals 1 to n, and it can be applied at an arbitrary point O of the body. The torque τ due to the force couple is equal to the sum of the cross product of the vector Ri and the force Fi from I equals 1 to n. In the vector products, Ri is the position vector of the point of application Pi of the force Fi with respect to the point O. We note that the resultant force F and the torque τ can be combined into a pair of vectors called wrench forming a six-dimensional vector used in screw theory, a mathematical formulation of forces and torques acting on rigid bodies. Then the theorem states that a system of forces acting on a rigid body can be replaced by a wrench. As already stated, the starting point of the torque vector τ due to the force couple can be at an arbitrary point of the body. We have also shown that the choice of another reference point O' still gives the same net force F but results in a different torque τ'. The torque is given by the sum of the cross product of the position vector Ri' and the force Fi from I equals 1 to n, where Ri' is the position vector of the point of application Pi of the force Fi with respect to the new reference point O'. We proved that this vector sum can be written as the cross product of the vector R0 pointing from the new reference point O' to the reference point O and the net force F, plus the sum of the cross product of the position vector Ri and the force Fi from I equals 1 to n. Since the second term is just the torque τ, we see that τ' and τ are generally different. As the figure shows, we can always find a new reference point O' such that the net force F and the net torque τ have the same direction, that is the net force is perpendicular to the plane of the net force couple. We can determine the cross product of this equation with the resultant force F for the torque τ' parallel with the force F. Then the cross product of τ' and F in the left-hand side vanishes, and the cross product of F and the right-hand side of this vector equation can be transformed into a linear system of the coordinates of the vector R0 describing the point O'. If we determine the components of the resultant force F and the net torque τ for a given reference point O, the linear system can be solved for the coordinates of the vector R0, and we can compute the torque τ' parallel with the force F.